What's up, guys? Hey, welcome and Merry Christmas to all. We finally made it to the Christmas special. Hope you liked the intro vid. That was kind of fun to come up with and do. Anyway, have to excuse my voice today if it kind of cracks or pops. I don't know, I caught something and it's just gone right into my chest. I've been feeling fine, but it's been in my chest and in my throat. So I've got my water next to me, and I'll try not to pop and crack my voice as much as possible, but just have to bear with me with that. Anyway, like I said, Merry Christmas, guys. Hope everyone's doing okay. We're going to be checking out how we put together all that remote functionality and all that fun stuff. So what we're going to look at is we're going to look at how the Raspberry Pi was wired up and configured. We're also going to look at how the Intel Edison, which was used in the outside light thing, that was an Intel Edison that was controlling that. We'll be seeing some videos and stuff of how I put that together. I'm going to try to keep this reasonably long, but it's probably going to get really long. So be prepared if you're in for the long haul, want to see how this is done. Like I said, this is going to be the most elaborate probably video that I've made so far, at least. So bear with me, sit back, relax, grab a cup of coffee, hot chocolate, beer, wine, whatever, and let's enjoy a whole bunch of electronics. So here we go. First off, we're going to look at the Raspberry Pi, how I configured that guy up for the motion sensor and whatnot for the Santa detection circuit, as well as how I was controlling the fireplace with it. So first off, let's check out our schematic here. So first of all, here's basically our GPIO header, and I think this is an old header actually, because I got to looking at like pin 25 is do not connect, which that's actually a ground. So anyway, don't know if this is maybe an old deal, but rest assured the pins are correct. So what we got going on is I've got ground, connected here, and it's going around and connecting to the ground of our PIR sensor. I've also got VCC connected to the 5-volt output. And then I've got our output, or for our PIR sensor, connected to this GPIO pin on pin 12, which I don't think it's 12. I think it's actually GPIO 10. But we'll look at it when we get into the software portion of it. Anyway, we got that going on. Then what I have done down here, you see a lot of this wrapping around stuff going on. I didn't actually get the tree, the Christmas tree portion built and coded. I figured it's going to be exact duplicate of how the fireplace works, except you'll just be switching an outlet. And I didn't have any spare outlets or extension cords or something to wire up to a relay. So it's not with that. But this is basically what I'm doing. Is I was unsure if in the webiopi system, if you could actually take and read the GPIO, like if you could change the TRIS real fast, the tri-state register real fast, and read it, and it still have the data buffered or whatnot in it. So I didn't know if you could do that. So what I did was I just you've got all these GPIOs. One of the GPIOs is going to be an output pin. The other one that's connected to it is an input. So like for instance, I believe it's pin 22 is actually the output pin. And then what I'm doing is I'm connecting, if you can see, pin 21 to that. And what I'll do is I read it. That way I can get a status of the pin, because obviously if we're going to control this through the web page, if you click on a button and it changes the state, the minute you reload the web page, you're going to lose where the state was. You don't know where it is. Like the minute you close your web browser and bring it back up, you're not going to know if it's on or if it's off, unless you try to save local variables. But then if you open the web page on one computer and then let's say close it, and then on your smartphone or tablet, you open it there, well, obviously the variables aren't going to migrate, right? Unless you store them locally on the host server or something like that. Anyway, can get complicated. So what we're going to do, sorry, I have to take a drink here and there because I'm afraid I might start coughing. Is what you have to do. What I did that was the easiest solution was just to wrap another pin around and turn it into an input pin. That way I can see whether it's high or low. Essentially, the output to our devices is high or low. That's basically all I'm doing here. So I've got a couple other pins for the outside lights, since I didn't get to the point where, I mean, it was tough enough getting that whole Bluetooth thing working, which is how that's done, is through Bluetooth and everything. And we'll get into that here in a little bit. But anyway, just getting that to work was a nightmare. So anyway, of course, you guys get the benefit of, you get to watch this video and you don't have to go through all the weeks and weeks of struggle that it took me to get the Bluetooth to work. But anyway, we take, and what I did was I did the same sort of thing. I'm just flipping a GPIO pin and then reading it back. And we're just, I mean, it's kind of an honor thing. I'm hoping that it goes out and turns it on, and then I'm going to say that it turned it on by flipping a pin high. Does that make sense? Hopefully that makes sense. So that way, because I'm not doing a callback, I'm not like having the Edison send something back to me telling me which way the pin is toggled. I'm just, you know, sending out the command to the Edison. Hopefully the Edison either opens or closes, does whatever it's supposed to do, and how I'm keeping track of what I've sent is by flipping a local GPIO pin high or low, depending on what I'm doing, and then reading that in to know what the previous command was. Did I open it or did I close it, you know, essentially. So that way when you refresh the web page, it will give you the same, it'll give you what the status is. Hopefully that makes sense. I'd almost have to show you, but hopefully that makes sense. And there's going to be subsequent videos to this. I mean, this isn't going to be like, I know you guys are going to have probably tons of questions. This is just going to be, I'm going to try to keep this as an overview video. Otherwise, this video would string on for hours and hours and hours. So I will go more in depth into this stuff and show you guys over the next few weeks how this exactly down to the nitty-gritty, how this is all put together. But again, this is just kind of a brief overview, assuming that you've played with a Raspberry Pi, assuming that you've played with a Intel Edison and got it going. The Intel Edison, I know, is fairly brand new, so you might not have as much experience as, say, the Raspberry Pi, but that's what I'm going to try for here. So that's basically how we're doing those GPIO pins. If you look over here, what we're doing is PIR sensor is pretty easy. You give it power, ground, and bring an output in. Label this as an input pin, and you check to see if it's high or low. And the way the PIR sensor works, in the past, if you've seen some of my videos, I have a video on the motion sensing camera. Basically the exact same thing, except instead of me taking a picture, I'm sending push notification through the weaved system. So anyway, just reading that pin right there. So you can go check that video out later if you want to. Then for the actual control of the fireplace, I've got a relay that I had. That, you know, you saw that in the video. There's a relay here. I'm switching that with a 2N7000 MOSFET. Now, there is a difference. You can't use like a 510A with the Raspberry Pi. The reason being, and the reason I say a 510A, the IRF 510A MOSFET, is that's one that you can readily get. You can usually get that if there's a Radio Shack in your region here in the United States. If there's one in your area, they usually most always will carry a 510A, which is an N-channel power MOSFET. The only problem is the threshold voltages. Remember, the Raspberry Pi, even though it has a 12 or a 5 volt output on it, that 5 volt output's actually coming from the regulator that's on board. That's not, or not the regulator, but it's coming from the USB connection. You know, the 5 volt connection when you put in, they just bridge it through. I'm sure there's protection on it, but they just bridge it through essentially. The actual, what's coming from the Broadcom chip, that BCM, 2835 or whatever that is, that's coming from the actual ARM processor, is only 3 volts. So that means all the GPIO on here is only 3.3 volts. It's not 5 volts. And if you look at the spec sheet for a 510A MOSFET, its turn on threshold, I believe, is somewhere around almost 4 volts. It's like, I can't remember, it's like 3.5 volts to 4.5 volts or something like that is its threshold to actually turn it on and turn it on hard. And so you won't be able to turn the FET on with the Raspberry Pi because it only puts out 3.3. 3.3 isn't 3.5, and yes, it does matter. 0.2 of a volt does matter. So, but a 2N7000, they're pretty good. I think they're, I don't know, 500 milliamp or maybe 300 milliamp or something like that, rated, drain to source current, but they're on their gate to source on voltage is only about like 2.2 or something like that, 2.2, 2.5, something like that, volts is all it takes to turn it on. With a max of 3 volts, you know, that you at least have to have a minimum of 2.5 to, you know, at least 3 volts to turn this guy on. Well, we've got 3 volts, so There's plenty to turn this FET on. So that's why I chose to use the 2N7000. And also the 2N7000 is very, very, very common. So DigiKey, Mauser, Newark, all those different places, they will definitely have. I think even Sparkfun Electronics has those. Everybody has those. Those are a very generally made. It's a very good part. So anyway, so that's why we chose that. Then obviously we've got a diode put in here for the relay. Those of you that don't know, relays are basically giant inductors. Whenever you collapse the electric field, basically turn it off in an inductor when you depower it. An inductor, you can't change the current across an inductor instantaneously with time. So what will happen is the voltage will fly to huge values to keep the current constant for, you know, however long it takes to deplete the magnetic field that's in these. So what happens is the voltage across this guy can get very, very, very large, and what that's called voltage flyback. And those of you that maybe have seen the old television stuff, the flyback converters, that's kind of what they're doing. We'll explain that in other video. But anyway, what this diode effectively does is this diode basically clamps the voltage here. It keeps the voltage from rising over, what is it, 7/10 of a volt or something like that. It can't rise over 7/10 of a volt higher. So if we got 5 volts, 5.7 volts is where this will clamp it. You know, it will keep the voltage from spiking. Because obviously if the voltage spikes real bad, it's going to tear up this little FET. This FET cannot take, you know, more than, I can't remember, I think it's 20 volts. Can only take more than 20 volts or something like that. Yeah, I think it's 20 volts. And it'll actually literally burn a hole through the oxide layer in these guys. It'll actually tear it up. So you wrap a diode around that. Pretty easy, just a 1N4007. Those are, again, very, very common parts is what I'm picking here. That's a really common diode. So just wrap that around there. That'll keep that from happening. When you switch this thing on and off, you can bang on it as much as you want. It won't tear up your FET. So anyway, that was something I didn't know. When I first got into electronics out of college, you know, I just thought, you know, the way college teaches you, a FET's a FET. You know, you put a FET in, it turns things on and off. Not necessarily. You get into the real world and you have stuff like this happens. So anyway, and then all I did, I've got one of those electric fireplaces, and literally it just has 2 wires that come out and then there's like a light switch. So really all you have to do is make or break those. You just make those 2 wires together or take them apart is what turns it on and off. So that's all I did here is I just put it on the normally open side of the relay, and it doesn't matter which way you hook it because you're just needing to put the 2 wires together to get it to turn on. And that's basically all that is. Very, very simple. Raspberry Pi connections, super simple. It's the software that's a little more complicated. And then let's move on to the Intel Edison. Now, for this, I forgot it's not behind there. I got to bring up the other one. Give me a second. There we go. Here's the Intel Edison's connections. Now, what I have done is the Intel Edison obviously uses that Hirose connector, which is a 72-pin connector, I believe. And it is micro miniature. It is teeny, teeny, tiny. In fact, I think the pitch spacing of the leads on it is actually, I think it's less than 1/2 of a millimeter. So you're probably not going to, you know, just solder wires onto a mating connector and plug them into a breadboard or something. I mean, that's probably not going to work. And I'm thinking of later on, I'm thinking of maybe having some stencils made. Those of you that don't know, a stencil is something you can lay over the top of a circuit board, and it has where the pads for a component to go punched out in the stencil. And usually they're metal, and you can scrape solder paste across it, and it basically masks off everything but the pads where you want solder paste to go. Then all you gotta do is drop the component down, hit it with a hot air gun, and it solders it down. It's actually really simple. I've thought about having maybe some of those made, depending on how much they cost. I may have some made and maybe post them on Tindy for you guys to purchase, and that way you could, you know, make your own boards and stuff that have this connector on it. However, the thing it's a problem with is I don't know if I would trust even scribing something yourself that's that fine a pitch. I mean, that's really fine, and you need like a Metcal soldering iron or something that's got some real power where the tip of the soldering iron gets hot, and you know, everything like that, because it's so tiny. You need special tools and everything. So how do we fix this? What's the solution to this if we can't really mess with that connector? The solution is Sparkfun Electronics has this very nifty Breakout block. They actually have quite a few different blocks for the Edison. They call it blocks. And they're different connectors, and they're actually stackable. There's actually, if I flip this thing over, this is the back of it. There's actually another connector on the back, and the connections actually pass through from the top to the bottom of the board. Another cool thing that they do is the Edison is a 1.28 volt device. So all of its GPIO, kind of like the Raspberry Pi, has 3.3 volts coming off of the actual chip. This one's even lower because they designed the Edison for like micro power situations, battery powered situations and things like that. So it uses way less. It's only 1.8 volts. Well, now that won't even trip a 7000, a 2N 7000 FET, right? It needs at least 2.2 or 2.5. I can't remember, one of the two. It needs at least that to trip it. So we run into that problem again. How are we going to switch anything? Well, the cool thing about this Sparkfun block is that they give you level shifters. There's two level shifters on here, and all the GPIO pins are level shifted to the 3.3 volts, which is fantastic. It'll take that 1.8 volts that comes off of the actual device and shift it up to 3.3 volts so you can actually use it. So that is very, very helpful. So that's basically what we're going to be using. What I've done is I've put together in Eagle basically a symbol that goes along with this layout that they've got. They basically brought the 3.3 volts, the 1.8 volts, and a lot of the GPIO pins, the system voltage and ground pins out onto a 1/10 inch spaced set, like header block essentially. So you can plug it into a breadboard, or you can do what we're going to do with it. So I recommend that. I'll put a link to that in the description so you guys can get to that. But basically, this is how we have hooked this guy up. Okay, so here's this breakout block, okay? And then there's that buck regulator. Let me actually call that up real quick. If you've seen my previous videos, you'll remember that I did that one regulator that I had that I did a video on, and it's basically this guy from IC Station. This little guy, if you guys remember that, we'll be seeing a video. Like I said, I'm going to show you how this is kind of put together in a later video, but which is later on in this actual video. You'll see some footage of that. But basically, you take it's a 20 watt, so it'll put out quite a bit of power. It's almost 2 amps. So you've got a 20 watt buck regulator, so we can put 5 volts in here and get the 3.3 volts out here. Because another problem that comes up with the Edison is, like I said, the Edison is created for micro power situations. What it does is you can't feed it 5 volts. It's only, I believe it's like 3.3 volt. Well, really it's 2 point so many volts, I think, is the lowest that you can power it with, up to 4.5 volts. You go any higher than 4.5 volts, you're going to damage the device. So the problem that we have is we've got a relay that's a breakout that's again from IC Station. Let me see if I can pull it up here. But I've got a single relay module that I use. Let me see if I can pull it up real quick. There we go. And I can put links to all this stuff in the video description. But it basically looks like this. It's a little relay module. But the relay is I don't know if you can see that, a 5 volt relay is what that is. So if it's a 5 volt relay, that means I need 5 volts. Well, the Edison can only give me, even with the level shifters, can only give me 3.3 volts. So again, we run into the same kind of conundrum that we need 5 volts. So that's what this whole circuit is going on with. I mean, trust me, there's a lot of stumbling blocks in this build. This build is quite intense. So what I did was I used a USB cord, because you can buy, at least I can get, you can get those little USB chargers that are like, I don't know, $10 or $5 that are cheap, that are good. They're 5 volts and they put out a reasonable amount of current. Like the one I got was 1 amp. So fantastic. So what I did was I used just a cheap USB cord, cut one end off of it, okay, kept the other end. It was the type A connector, you know, the big connector that like plugs into your PC or will plug into one of those wall chargers, okay? And I cut the other end off of it off. I'm only using the voltage lines. There will be a black and a red wire, and those correspond to black being ground, red being power. And you'll get your 5 volts and your 0 volts. What I did with that is bring that in to that little buck regulator that was from IC Station, that little guy, okay? Bring it into that buck regulator. That's what this guy is. And then output set that buck regulator because it has a setting on it. I don't know if you saw that, but it actually does have a setting on it. That let me see if I can get that back. There we go. And it has this little potentiometer. That's what you turn to set the voltage, and it has a nice little digital readout. Like I said, I reviewed it in another video that you guys can look at later. But anyway, that little guy is right here. So I set it for 3.3 volts. Really, it should be, I put 3.3. It should be about 3.6 because we're going to be using the onboard Wi-Fi and Bluetooth modules that come with the Intel Edison. They require quite a bit of power, and they can pull the voltage down if you're not, you know, if you're not watching it. So I set mine a little higher. We did like 3.6, but I think 3.3 probably be all right. But I did mine as 3.6. Like I said, it can handle up to 4.5 volts. So you know, a little more oomph is all right. So that's what I do. You bring that to the ground and VSys pins, okay. And then over on the other side, we've got the relay connected up. I used the GPIO pin 128, and what this is if you buy an Edison, you will get a basically a little board that you can snap the Edison into that has all kinds of stuff. It's like a dev kit. It has just all kinds of buttons and everything else, and it also has the same header configuration as the Arduino, and it actually can use Arduino libraries. We're not using them here, but perhaps in later videos I'll show you how that works. But you can actually use your Arduino sketches and load them onto this or develop with the Arduino IDE if you want to make a real simple solution that is micropower. Anyway, if you're looking at it, I used IO3 on the Arduino-ish like header. It's the IO pin or 2. IO pin 2 is what I used, which corresponds to GP 128 on the actual Edison. So, and you have to know what the actual Edison's number is because remember, there's that Sparkfun block. If you look, it goes by the GP, the GPIO that's on the Edison. You know, it doesn't really go by the Arduino like, you know, style headers, that numbering. It goes by its own internal numbering. So, and then you can kind of, I don't know if you guys can see that, but GP128 is right here, is what that is. So that's the one that we chose, GP128. And basically we're doing the same thing. Since this is only 3.3 volt, even though this is an active low relay, that relay that I was showing you is actually active low. It has a little MOSFET buffer in between. It's still 5 volt. So when you try to pull it down with this guy, it doesn't work right at all. I could try to explain why, but anyway, it won't work if you do it that way. So you're gonna have to buffer it as well. Since there's 2 different voltages, and you could take a chance on maybe hurting the Edison. So what we do is we buffer that with another 2N7002, because remember, it works at 3.3 volts, right? And these GPIOs are level shifted to 3.3 volts using that breakout board. Okay, so we're doing it again. We're just using an N channel. We're bringing it to the output of that relay. We're giving a 1 megawatt or 1 mega ohm bleeding resistor. Use 1 mega ohm or something pretty good, maybe 500K or something pretty sizable, because I tried using 100K and it's just with 3.3 volts and 100K, it robs too much current. It just doesn't work right. So I used 1 meg just to be safe. Works fine, but that's your bleeding resistor to, you know, bleed off that gate capacitance. So anyway, put that sucker in there. Ground this thing, add it to the 5 volts, so you'll bring it to this side of the regulator, not this side. You bring it to the 5 volt side, and then that way, when this switches it, when you turn this on, it's gonna pull that down, and it will activate the relay. So pretty simple. Things we got going on are actually really simple and pretty straightforward. So now let's go ahead and log in to. Let's start with the Raspberry Pi. So let me get over here. Let me get my putty out here, and we'll log in to the Raspberry Pi. So let's grab it. Pi, Raspberry, doodly. So we'll log in to the good old Raspberry Pi. So now, again, I'll probably go through other videos of how to actually build all this stuff and set all this stuff up and everything. But for right now, I'm just going to show you, if you had everything set up, what to do. Okay guys, alright, what we got going on here is I got my Raspberry Pi in one window and my Edison in another window. Like I said, I'm just going to be showing you where to put the scripts and how to run them all and get everything set up and running. I will do subsequent videos on how to actually build all those scripts and build everything and what actually is taking place. It's just that, I mean, I tried recording all that and it's going to make this movie like 2 hours long, so it's going to be way too long. So I'm just going to show you how to get them on there and make it work. So what I'm going to be doing is, the way I usually like to get these on here since SSH is configured is using WinSCP. Check out that. If you don't have it, go download it. Just type WinSCP in Google and you'll find it. Download it. You type in the IP address, your username and password and whatnot for your different things, and it will log you in. Okay, right now I'm using PuTTY. You can do the same thing with PuTTY. Download, or at least to be able to shell into it, use PuTTY. That's what I'm using. So, but to transfer files, WinSCP is a good way to go. So what I did was, in my home directory on my Pi, I created a cd webiopi directory, and then I put the www file in there as well as the detect.c file, and then I made an executable of the detect. I can't remember if the executable is in the zip or not. If not, you can just put the source, the .c, in there, give it a gcc-o for output, name the executable file detect, and give it the source file, and that will compile it for you. It's a very simple program. So that's that part. In the www, that's where the index and images file is, so you'll use that, as well as you'll probably want to vi the index and go in here, go all the way to the bottom, to the bottom. I think it's in here. Yeah, and you'll want to use this location. You'll want to change this reference. You want to change this IP address to what IP address your Raspberry Pi is. So you'll want to change this IP address here and here. And that's the two places you need to change it in that file. Okay? And then that should work just fine. Now, there's also the CGI directory for those .sh files, the BT activate and BT deactivate. You're going to go to usr lib cgi-bin. Okay? And in there, that's where you're going to drop the BT activate and BT deactivate. Now you want to make sure and do a change mode 777 on both of those. BT on the BT activate like that and hit enter, and on the deactivate, because you want to add the ability to execute them. Okay, so that way the web page will be able to execute these shell scripts. And similarly, you want to VI these, both of these, and there will be an IP address in these as well. So you'll want to take and change that to your IP address for your Raspberry Pi. And that one, as well as the deactivate script, will need to be done that way as well. So there you go. So change that, and those should be squared away, ready to go. Okay, and then we are going to have to set up the Bluetooth. Now, there's going to be a command that you'll run. I'm going to go back to my home directory. There'll be a command that you'll run. I'll put it in the description along with a link for the stuff you need to install. You need to install the bluez. Also, there's the HCI tools and other things you have to install. I'll put the command down there in the description too. I'll put a link to the document link that showed me where that was and how to download it. But basically, you're going to use a USB dongle. I don't know if you saw it in the videos and stuff, but there's a USB dongle that I have plugged in to my Raspberry Pi, and you'll need to download the Bluetooth stack and things like that for it. And like I said, the command is down in the description, as well as the link to where it talked about where I found out what that command was. Once you install all that stuff, you just do the apt-get install and put all that stuff in there. Then you will run these commands. You're going to go over and you're going to do a sudo rfcom 0, and now we need the Bluetooth address of the device that we're going to type in. So I'm going to skip over to the Edison, okay, and this is assuming the Edison is up and running, you've got Wi-Fi enabled and things like that. we're going to go to the Edison, and to enable Bluetooth, we're going to perform an RF kill unblock Bluetooth. That's going to unblock it. Then we need to turn it on. So we're going to do an HCI config HCI 0 up, and that'll turn it on. Okay, so that's got it on. Now we need to put this guy into listening mode so that when we do our RF comm over here, we'll be able to listen for it. And actually, I did that command wrong. This should be connect 0. Because that's using device 0. You could have multiple Bluetooth dongles plugged in, and it'll label them device 1, 2, 3, 4, and so on. Since I only have one, it's device 0. Same as over here. We're going to do an RF comm listen device 0, because this only has one Bluetooth device on board, so 0, and in channel 1. And we're going to give that an ampersand. Okay, we're going to run it in the background. So it's now waiting. So now this one, and make sure you do the sudo because it'll mess things all up. In fact, I think this guy reboots and does weird stuff if you don't. So use the sudo. Now we need this guy's Bluetooth address. To do that, we just type HCI config, and it'll give us the Bluetooth address. So now we're going to type that in. And 1A, and channel 1. And we're going to also start that in the background, okay, with an ampersand. Now we should see them connect. There we go. So both of them are connected now. Now to test it, we're going to come over to the Edison, and we're going to cat our device RF comm 0, which that will basically just, it opens up that device, and anything we send to it, it should appear here in this window. So now we're going to echo something, hello world. We're going to redirect it to our device RF comm 0 that is on the Raspberry Pi. Excuse me, I'm going to get a drink of water. Okay, now for some reason it puts out a bunch of barf, and I don't know why. But if you just re-echo the command a couple of times, it stops it. And I don't know what that is. But anyway, that's how it works. So this will echo anything. So we echo. Right. All right. See? So we are connected. It is sending that via Bluetooth to the Edison. So now that our Bluetooth is all connected, we can now run the scripts that we need. So we're going to Control-C out of that. We're going to go into the Edison and perform an ls. Well, here, let's just do an ls. And you've got two scripts. You've got the setup IO2, which sets up IO pin 2, and remote.sh. The setup IO2, I've got some like debug stuff in there, so it'll probably give you some funky stuff, but don't worry about it, it sets it up. Run this first, see, it gives you that junk. And then run the remote command. And what this does is this sets up the to control the relay, the way we've got it hooked up in those diagrams. So now if I echo a C for closed to device RF comm 0, we get it closed over here, and I've got it plugged in behind me. I can hear it close. I can hear the relay click. Similarly, we give it an O, it opens it. So C for closed, over open. So that works. So now we're ready to test our web page, but first we have to give our web page permission to this device. So we're going to cd to the device directory, and we're going to do our famous, in fact here I'll just show you ls rf comm 0, oh whoops, ll. As you can see, there's no read write on everybody. Now, I know those of you may say it's not good to put permissions this way. I'm just showing you guys that it's working. You could add it to the group, dial out, and things like that, but I'm not going to cover that here. Excuse me, got to get a drink of water. So what we're going to do is we're just going to change mode, 666, RF comm 0. Now, oops, we got to sudo it. So now, if I ll RF comm 0, I get read write on everything. Okay, so that's what we want. So now let's give her a shot. Let me bring up our web page right fast. I may have to. I'm getting a web page unavailable, as you can see. So we may have to restart webiopi. Not a problem. Etc init.d. We're going to sudo service webiopi restart. So that restarts it. You can even do a quick status. Looks like it's running. So now I'll bring this over. I should be able to refresh this. I may have to open a new tab. See if he'll do it. Yeah, let's just start over. Let's open a new tab. Okay, there we go. That was what it was. My browser needed to be refreshed. Okay, so now we should be able to control it. And there it is, closed and open. Closed and open. And I can hear it clicking behind me. So that's basically all you have to do for that. So that sets that up. Now, the last thing is the Santa Claus detector. So let's go back to our home directory, cd to our webiopi. And now all you got to do is ensure that you have executable on your detect. So you could change mode and do like +X and detect. And that'll do the same thing. That'll add executable to it. Gosh, I got to get a drink of water. Sorry guys, my voice is failing on me. This is like the third time I've recorded this video. Alright, here we go. /detect. Oh, we got to sudo it. So now I'm going to go run over here and I'm going to wave my arms in front of the sensor and it should detect it. And what you should see is the data for it sending out the push notification, as well as a timestamp and the message Santa has been detected or something like that. Okay, here we go. Alright, so there we go. So there's the message going out to my device, as well as the Santa being detected. My device is lighting up over there, so it actually made it. So that's how you can send a push notification from a trigger of a GPIO. So there you guys go. Like I said, all the source code and everything will be on my project code link. So go check that out, download the zip. Feel free to sift through it, make changes to it, edit it, modify it, do whatever you want with it. It is totally for you. It's my Christmas gift to you guys, all right? So with that, guys, I think that's probably it for this video. Hopefully this didn't go way too long. But anyway, there we are. I'll be having additional videos that will show you guys more and more how to actually set all this up. They will be way more detailed, and I'm going to break it up into subsequent videos just because it's just too much information to cram into one video. You guys are going to be bored to tears already with the length of this video. You don't need another hour or 2 hours added on to this. So anyway, I'm going to leave you guys with some footage of me putting it together physically, building all the stuff and putting all of it together. And guys, Merry Christmas, Happy New Year, Happy Holidays for those of you others and everything. Have a good, safe holiday. You guys take care, and remember, keep coding, keep building, because that's what it's all about, is the fun of electronics, guys. Take care. Thank you so much for all your support. Hopefully you enjoyed all this, and I'll leave you now with some of the footage of me putting it together. Take care, guys. Like, subscribe, share. Follow me on Twitter and Instructables. I'm out. That ought to do it. See ya. Okay, guys, here is the Raspberry Pi setup that I've got going on. Kind of a rat's nest, really, but I've got the PIR sensor right here. Now I wrapped some tape around it because it's kind of got like peripheral vision, and so stuff that's like out here on the side would actually trip it. So I wrapped some tape around it where you have to be pretty much directly in front of it, or at least pretty close to in front of it for it to actually work. Got our relay, got our 2N7000 transistor right there. So there it is with the bleeding resistor and whatnot. Got that all hooked up. This was actually, I got some hookups. These were just some other hookups that I had. But you can see where the GPIO was connected. The two are connected. There's one of those wires that's coming to here is for the in. One is for the out. Okay, so it's how that's all working. So anyway, I got that going on, and you can see, you know, with as you saw, you know, before, you can see that it lights up whenever it sees something. So that's basically how, and see how it has a delay before it actually moves. And so before it actually goes back, you can see that. See the light turn on, and then it should turn off. There it goes. So it has a delay. So that's what that while loop was for. Then I've got the relay set up here that comes across, and I wasn't able to get a nice plate for it, but I've got over here, let me back off here. This is where my, if you take this off, this is where my fireplace connections are. I just crimped on some connections, and you can see the connectors. And you just put those two wires together, and it starts working. So that's basically how it works. And then of course the fireplace is right over here. You know, it's one of those electric, you know, you can see the pilot light down inside there working. So anyway, that's what it does. It just turns on a valve, lets the gas roll in, so it'll start, so it'll fire back up. So anyway, guys, that's basically the behind-the-scenes look at this thing. There's the over there. See that gigabyte? That thing is so old. That's unbelievable that Bluetooth stack recognizes that, because that sucker is old. And then underneath it, you can't really see it, but underneath it is the Wi-Fi module that's in there. So anyway, and yes, there's the camera off to the side. And I know some of you will probably be like, well, there's a camera. Why didn't you set the camera up so you could see Santa Claus? Well, I'll leave it to you guys to set that up. How's that? All right. Okay, guys. Doing this kind of off the cuff here, but we've got the Intel Edison. We've got it all programmed up and whatnot. We've also got a relay. This is going to be a 5-volt relay, but it is an active low, so it should, we can use the Edison's 3.3, but its pull downs to activate it. This is actually pretty cool. This comes from Sparkfun Electronics. This is a Breakout board. I'll put a link down in the description, but this is the Breakout board that pulls the GPIO and the power and everything out of this little tiny Hirose connector and brings it out to these boards. Also, these little pieces that are on here, those are actually level shifters. So it'll actually shift it from the 1.28 volts, I believe, which is the Edison's voltage, to the 3.3 volts that is normally used on the GPIO. And then what we're going to do beyond that, since this is an active low connection, it does work just fine with this guy, but it needs the 5-volt input to make it work. It's got, I think, a little P channel FET on it, which does the active low type stuff. But here we've got our voltage regulator that I showed a review on. You can check my videos for that, but there's a review on this. But this is just a voltage regulator. I liked it because it had these little standoffs on it and everything. So what I did was tape up the back, and then I've hooked a USB cord in and just used the power and ground from the USB cord. It's coming into, we always called these a bell box, but it's basically going to be one of those watertight boxes. In fact, here, let me walk over here and get the lid. Okay, I grabbed the lid. It's one of these. You know, you usually see these outdoor boxes, what we'll put the receptacle in. But this is going to be the receptacle unit that will, you know, that, like I said, that will work outside. So anyway, so we need a relay to control the power to the receptacle and whatnot. But like I said, we got to have 3 volts and 5 volts going on. So what I'm doing is I'm bringing a USB cord in. I'm going to use one of those USB wall warts. You see that? Just got one of these quick little USB wall warts. Basically takes the 120 volt, turns it into 5 volt DC, and then what I'll do to regulate the voltage so we can use the Edison, since the Edison only takes 3.3 volts max, we'll build 3.3 volts with this little regulator is what we got planned. And then I'll also tie onto this with the 5 volts to come over and hook up this relay. And the idea is that I've drilled some holes in the bell box. As you can see, I've drilled some holes in the back of it. And I'm going to mount with these little screws. I had to use a nut because these screws were too long. But to mount this guy will mount like that in the bottom of this. And then I'm going to use the Edison. I will mount it in the side of this thing. It'll be on the side, which is where the Edison will go. And then the relay, I believe the relay should set, if I can get this back up in here, this will all bend that back out of the way, and the relay will go in here and set down. Well, kind of sort of. It's going to be better when I'm not doing this one-handed. But it'll basically sit inside there and plop down in the front of that is where that's going to go. So it should all come together. I'll give you kind of some videos. I don't know if I'll do progress videos, but we'll come back when it's all put together. Okay, guys. Got everything put together here. Got the regulator mounted. The Intel Edison, he's off to the side here. Ended up having to put a 2N4007 in there to buffer it, since this relay is 5 volts and the Edison only puts out 3.3 volts. Had to buffer it with that. But other than that, I'm going to mount this in there and we'll go test it out. Pretty cool. Okay, it's a little bit cold outside, but I've got a little sleigh and a tree. Let's see here. These are a little choppy. And then I've got the house. See that? I got the house there. Everything is off. I got the kit installed. There's the box. It's plugged into my time clock, so it has override and plugged in. The other one, the USB one's plugged in as well. So what we're going to do now is we are going to get our device here and we are going to turn this on. So here we go. See it? Push it. I heard it click and the lights are on. That's pretty cool. So hooray. Merry Christmas to all. That's basically how she works. Alright guys, it is cold out here. Christmas lights looking good. And I'm out. See you guys.